Hello everyone, I am Yayati Gupta, and in this lecture we are going to talk about the cascading behavior in networks. It is your chapter 19 in the book Networks, Crowds and Markets by Klinberg. So the agenda of this talk is, first of all, we'll look at the human tendency to follow each other. Does humans have this tendency to mimic or follow each other? Next we'll look at how can we model this diffusion phenomenon over networks. Next we'll look at the impact of communities on information cascades and the theory of weak ties. After which we'll talk about certain extensions of the basic cascade model. Next we'll look at how do people take collective action using knowledge and thresholds, and finally we'll discuss some advanced material. So how many of you think that we do really follow or mimic each other? Humans follow and mimic each other, and to our intuition all of us somewhere know that yes, we follow and mimic each other. You can go watch both of these YouTube videos mentioned here and then come back. These videos give you very subtle examples. Rather the second one is more scientific one, which shows you the tendency of humans to look in their environment and then they start doing what other people in their environment are doing. You may have many personal stories in which you would have seen that you were going on a right path and then you looked around the people and they were doing something else, and you sort of also thought that they are doing it right, and you changed your way from right to wrong looking at other people. So I have a very nice story to illustrate this. When I was a biology student in class 12, we were having a lab test. So the test was about to look into the microscope, and then we had to identify what was there in the underlying slide. So some students looked it in and they came to the conclusion that it is some phase of cell growth. So some of them said it is anaphase, some people felt it is prophase, and then soon whole of the class involved in a big fight because some people felt it's telophase, some felt it's anaphase, some felt it's metaphase, and so on. So all of us have written totally different answers in our answer scripts, like anaphase, telophase, and so on. Next day when our biology teacher, she entered the classroom, she was very angry with all of us, and the reason why she was angry was the slide was a hydra, which is a microorganism. So this anecdote in itself tells us how do we tend to follow each other, because everyone around us was thinking that it is some stage of cell growth. So we finally reached to the conclusion, we not even once thought that it could be something else, it could be a hydra. Another very nice example for this is when I was in my BTech in like 3rd or 4th year, I was very confused about what career pathline should I choose. Most of the students around me, they were running for an MBA or they were going out for jobs. But I had a different plan in my mind. I wanted to do higher studies. So most of the time whenever these people met me, they made statements like, you'll always keep studying, or wouldn't you get bored, and do you not you are going to do a PhD, do you not want to get married? And I also really felt scared sometimes because of their statements, because everyone around me is going for a job and MBA, and I'm the only one in the class who is after higher studies. I still remember a day in my class where a teacher asked her whole class that how many of you want to be a teacher, raise your hands, and I was the alone who has raised my hand. So all these things, they put me in a kind of trouble, because when I look at other people, I also feel doing like what they are doing. I feel like that's the right way to go. But thanks to my dad and the supportive teacher who has shown me the right path, and I'm currently quite happy with what I am doing. So that is a way we follow or mimic each other. So most of the time, now the question is it always good to follow or mimic each other? And if it is not that good to follow, to mimic or follow each other, then why do we follow each other? And the answer is, following each other gives us some benefits in several cases. So first type of benefit it gives us is the informational benefit. Suppose I am a farmer growing up my crops in some village, and a new crop comes into the market. In that case, I can't stand alone. I have to get along with everyone. I have to listen to them. I need this new information on how to use this crop. So in this particular case, I need to follow others and I need to do what they are doing. Another case, suppose I am a doctor and a new drug comes in the market. The same thing applies here. I need to know how this drug is used, and again in this case I need to follow others. So one reason for why we follow others is the informational benefit. Yet another reason for it are the direct benefits. A direct benefit is something like, I say you that if you spread a rumor about this girl in the campus, I'll pay you 10,000 rupees and you do my work. So here you are doing my work, or you are following me, because following me is giving you some direct benefit. A very good example of this is, if you do remember, was there was this Hike Messenger. I guess it's still there. And to promote their campaign, what they did, if you would invite some of your friends to hike, you will get some extra talk time in your phone. So here you are getting some direct benefit in following this new technology. So this is the second reason for why do we follow each other. If following some other person give me some direct or explicit benefit, I am going to follow him. So through all these things we see that following each other, following other people, it can give us benefit or it cannot give us benefit depending upon the circumstances. So we should be wise enough to know in which conditions we should follow others and in which we should not. Yes, one more very important point to make here is, please notice that when we are looking at other people and following them, it is not the whole world that we follow. These are only the few individuals around us who are close to us, that matter to us in making our decisions. An example of this is, suppose whole of the world starts using Apple or say Ubuntu, and we in IIT Ropar, the faculty places a restriction that we are going to use Windows and nothing else. So whole of the world outside is using Apple or Ubuntu, but all your faculty members and all of your friends are using Windows for every single task. In that case, even if Apple or Ubuntu may be a good technology, but you will be forced to use Windows because everyone around you is doing so. So this gives a rigor to the fact that we are influenced by few and not whole of the world. Okay, so now let us try to model this diffusion process. Modeling this diffusion process is a very interesting phenomenon on its own, and we are going to take it in terms of some game theory. So we call it a networks game. So generally what happens is, the kind of modeling that we are going to do is, you will have two options. For example, you may have two technologies, technology A and technology B. Now depending upon what your friends are using, you need to decide which technology you are going to use. So a very simple example of it is what I show you here. Suppose a person is here in the middle. Let's say this person is me. Now I have my friend invites me out for a party. So if I go out with my friend, I'll get some payoff. Payoff means I'll get some advantage in going out with her. Maybe we'll enjoy, we'll blow our stress out, we'll do some shopping, we'll eat some nice food. So that is the payoff I'm getting in getting out with my friend. But suppose at the same time my friend, she gets some problem in her research and she wants me to sit with her and study and solve this problem. So in this case also I am doing some other activity with the same friend. So we are sitting, we are reading and we are troubleshooting the problem. It is giving me some different payoff in terms of my researching and troubleshooting capability. So if I have to make a decision between the two, I will see which one of these is giving me a higher payoff and take that action. And if I do none of these activities with my friends, I get a payoff of 0. On this basis, we design a matrix. Let us say we call both of these actions by two variables, say action A or action B, or say technology A or technology B, and V and W are the two friends. So you see here, if V and W, both of them use this technology A, both of them are going to get a payoff of A. If V and W both use this technology B, both of them are going to get a payoff of B. But if V uses B and W uses A, then they get no payoff, and vice versa. If W uses B and V uses A, in that case also they do not get any payoff. So we call this AB coordination game. So in this case, A and B will try to do a thing which will give them the more payoff. Now what the situation that we are dealing with is a bit complicated. We do not have only one edge. I do not have only one friend. I have a number of friends. So the actual scenario is something like this. So I am somewhere here in between. There are 4 of my friends who are very excited about going out. 3 of my friends are very excited about studying. Now if I do study, I get an payoff of say some amount. I get some payoff from all of these 3 people. And if I go out, then I get a payoff from these 4 people. So now we can see it not only depends upon the payoff being given by a particular action, but it also depends upon your number of friends choosing a particular action that decides whether you are going to do that or not. Let us say in this case, payoff for going out was small as compared to the payoff for studying, but maybe the number of my friends going out is so large that I ultimately choose to go out because cumulatively I get more payoff for going out. So let us try to model it. So here is a node V. The degree of V is D. So V has small d friends. Now P fraction of D's neighbors use A. So these are the P fraction of V's neighbors which are using the technology A, and the rest of the neighbors, that is 1 minus P into D, are using the technology B. So the payoff that the node V is going to get from all these friends will be P into D into A, and the payoff that it will be getting from the people here will be 1 minus P into D into B. Now if V wants to adopt the technology A, so the payoff it gets from the people who are using A should be greater than or equal to the payoff it gets from the other side. So we get here P should be greater than or equals to B divided by A plus B. It simply means that if greater than or equals to B by A plus B fraction of my friends are using the technology A, then I'll also go ahead to use the technology A, and we call this particular value as the threshold Q. So this threshold defines the minimum fraction of my friends that should adopt an idea in order for me adopting that idea. Let us try to solve an example based on this model. So suppose this is the network given to you. In all this modeling, we'll first assume that every node in the network has adopted the technology B. So here every node in the network has adopted technology B. Then some node in the network adopts the technology A. So say in this case W is the first one to adopt the technology A. Now next we see how will the cascade occur. So in this case, if W adopts the technology A, and let us say V also adopt the technology A. So V and W are the first one to adopt the technology A. If we calculate the threshold in this case for adopting A, it will be 2 divided by 5, which will be 0.4. So if 0.4 fraction of a node's neighbor adopt the technology A, they will also adopt the technology A. So in this case, if you will apply the model, you will see that after V and W, R will see that out of its 3 friends, 2 have adopted the technology which is greater than its threshold. So in the next stage, R will also adopt A and T will also adopt A, and in the next case, S and U will also adopt A. So ultimately in this case, whole of the network is finally going to adopt the technology A, and the network becomes stable after every node has adopted A. Now here is a question, and the question is, there are some ways for network to become stable. One way of stability is everyone has adopted B, the process has stopped and no one is adopting A. Second possible stable state is everyone in the network has finally adopted A. I have one more stable state. Is it possible that both the technologies A and B, they coexist in the network? That is, the cascade starts and it stops at a position where some part of the network has adopted B and some part of the network has adopted A, and now no one is going to change his or her decision. So let us see with the help of an example. So this is the network shown to you here. So let us say the thresholds are same, a equals to 3 and b equals to 2. In this case, what if I tell you that 7 and 8, let the nodes 7 or 8 are the first ones to adopt the technology A. So can you model this phenomenon and then see ultimately what part of this network is going to adopt A and when is the cascading process going to stop? So if you have done it correctly, you will find out that ultimately all of these nodes 4, 5, 6, 7, 8, 9, 10 they adopt A, and just at that process your cascade stops. So no other person in the network adopts A and the process stops here. So here we can see a coexistence of A and B in the network. There is a more subtle point to be noted here, and the point is we can see that this network is divided into some form of clusters where 1, 2, 3 are forming a cluster of their own. These nodes are forming a cluster of their own, and these nodes are forming a cluster of their own. So we can see that it is getting difficult for an information to go outside the cluster to which it belongs. So we can build a statement from there that clusters are an hindrance to the information flow. Why does it happen? Why did this technology stopped growing? It was because first of all clusters were a hindrance to the information propagation, and a more deep fact that lies here is people fear taking risks. So no one wants to take risk in their life. So we know that if a new metro starts today, we'll call some VIP people to inaugurate it and whole the process will go very smoothly. But I don't know how many of you know about this fact that when railways were first started in India, so it was a very new concept, a very new thing that came to India. We haven't seen any such thing before in our life, and people, they were so scared to sit in the train. Leave VIP people, even common people, they were not ready to sit inside a train for its first ride. In that case, what officials had to do, they had to ask some prisoners to sit into the railway lines. Not ask, they had to order some prisoners to sit into the railway lines to prove to rest of the population that it is a safe technology. Again, why it happens? Say a scientist invests 30 years of his life developing a time machine, and after he has finished forming the time machine, he is the only one who is supposed to sit in it. What if a scientist comes from NASA today in our college and asks one volunteer to sit in his time machine and then see what happens? It is very sure that no one will get ready. It's because it's taking a big risk. But then imagine a very high-tech world where you see everyone around you gets in a time machine once in a while, goes back 5 years back in their life and then change their life for a future. In that case, I'm quite sure you will not be afraid to adopt this new technology. So we need some bold and daring faces to adopt some technology in the starting. Okay. Now, what do we want? We have already seen how communities were hindering the spread of information, and we have seen the coexistence between two technologies A and B in our previous example. So some practical examples for this coexistence are dominant political views between adjacent communities. And one more example is, like we discussed before, if IIT Ropar uses Windows, you will be forced to use Windows no matter what whole of the other world is using. Now, what if A and B are competing technologies and A does not want to be stuck in between? As we have done in our example, we saw that A got stuck in between. But in our case, A wants the entire network to be its own. So one way to go about it is, A should increase its quality. If A increase its quality, so the payoff associated with A will increase and probably the threshold will decrease. So in the previous example, try changing A from 3 to 4 and you'll see the value of threshold going down from 2 to 5 to 1 by 3. So now instead of 0.4 fraction of your friends, only 0.3 fraction of your friends are needed to be infected to infect you. So can you apply this model after changing A from 3 to 4 and then see what happens? what if I cannot increase A's quality? I say that A's quality is already as best as it can be. So I need some other idea to keep my cascade going, and the idea is somehow you convince a small number of key people in the part of the network which are using B to switch to A. Such people, please notice, needs to be chosen very carefully. It's like if you want a new bike or scooty, convincing your mom or sibling will not help you. You should convince the chair of your home, that is your dad. If he agrees, even if others were in opposition, the two will agree. But it will not happen the reverse way. So you should choose the right people to adopt your technology. So in the previous example, if you convince node 12 or 13 to switch to A, your cascade of A may start again. Such cases are most important in viral marketing, where you should intelligently target the influential people in the market to adopt your product. So now let us try to model the impact of communities on the information cascade in detail. So for that we need some terms to be nicely defined. So first we define the term cluster of density P. What is a cluster of density P? We say that a cluster of density P is a set of nodes such that each node in the set has at least a P fraction of its network's neighbors in the set. So it simply means that we say that a cluster is of density half if in a particular set of nodes, every node is such that half of its friends belong to the same set. Then we call it a cluster of density P. Let us try to look it with the help of an example. So can you find out the cluster density for these three clusters? So if you see in the case of D, it has 3 friends out of which 2 belong to the same cluster. C has 3 friends all of which belong to the same cluster. A has 2 friends both of which belong to the same cluster, and B is similar to C. So the limiting case is D, and we can convince ourselves that the cluster density for this cluster is 2 by 3. Similarly, the cluster density for this cluster is also 2 by 3. One more thing, if you are not aware with the concept of clusters and communities in network science, you can go to this YouTube video. It's a 6 minutes video. Watch it and come back to revise your concepts. Okay. So now consider there are a set of initial adopters of behavior A with a threshold of Q for the nodes in the remaining network to adopt behavior A. It is very similar to what we were doing previously. Now the lemma states that the remaining network, if you're okay, so now A, it starts cascading over your network. It cascades on some of your network and then the cascading process stops. I want to see whether there is a complete cascade in the network or not. Complete cascade means at the last every single node in the network should have adopted A. The lemma says that if the remaining network contains a cluster of density greater than 1 minus Q, then your set of initial adopters cannot cause a complete cascade. And the reverse way also. It says that if your set of initial adopters can't cause a complete cascade, it means that the remaining network contains a cluster of density greater than 1 minus Q. We are going to prove this lemma for one way, and it's quite simple to prove it, so I would like you to do it the other way. So let's look at the one way proof. Suppose a network contains a cluster of density greater than 1 minus Q. So I have to prove that a complete cascade on this network is not possible. So let us prove it by contradiction. Let us say that there is a cluster of density greater than 1 minus Q in the network, and let us assume that the complete cascade happened, and then see what happened in this case. Now we know that whole of the network got infected at last. So if we look at this cluster which is having density greater than 1 minus Q, it is also completely infected at last. So let us say there is a time t where the first node of this cluster was infected. Let us say this timestamp to be t, And let us call this cluster having density greater than 1 minus q to be cluster X. Now there was a time when the first node in this cluster was infected, and we have said that this time is t, and let this first node be u. So u is the first node in this cluster to get infected. Let us say the degree of u is d. If u adopts the technology A, it means that the number of neighbors of u at that time who have adopted the technology A should be greater than q into d, because q was the threshold for adopting the technology A. It means more than q into d of u's friends would have adopted technology A at that particular time, right? Moreover, we know that u is the first node in the cluster X to be infected. No other node in the cluster X has yet adopted A. It means that rest of the friends of u have still adopted B. And what is the number of rest of the friends of u? We know that u belongs to the cluster of density greater than 1 minus q. It means that the number of neighbors of u which are inside the cluster and who are still adopting the technology B, that is greater than 1 minus q into d, according to the definition of your cluster density. So we get both the kinds of neighbors of u, those who have adopted the technology A at that time and those who have adopted the technology B at that time. And if we find out the total number of neighbors of u by both of these, it will be greater than q into d who have adopted the technology A plus 1 minus q into d who are still on the technology B, and this value turns out to be greater than d. But we have taken the degree of u to be d, so this thing is not possible. Hence we have proved by contradiction. Next, just give me 1 minute. Next, let us try to look at the importance of weak ties in information cascade. So I guess most of you will know what is a weak tie. Weak tie is one of the most interesting concept in the field of social networks, and for giving if you do not know this concept, you can go to this YouTube video and watch it. To give you a small example of what a weak tie is, consider your best friend in this network. Sorry, not in this network. Consider a best friend in your hostel, and then consider a friend of yours with whom you studied in your second grade. So you have both of these friends. With whom do you think you will be having a stronger relationship? It is quite obvious, the friend with whom you spend most of your time, who lives with you in your hostel, he is having a strong relationship with you. Now, so we call this particular kind of tie as strong ties, and the ones that you are having with your friend who was with you in second standard and with whom you talk rarely, we call that as a weak tie. Now Granovetter carried out this very interesting experiment. He tried to look at from where do people get their jobs. Is it through strong ties or is it through weak ties? And most of us would think that it is through strong ties, because the people who are closest to me should help me getting a job. But what he noticed was totally different. He has observed that it was the presence of weak ties that helps you getting a job. Let's try to see why does it happen. Generally, the people with whom you share strong tie, they belong to you, they are like you and they belong to your community. So generally there is no new information flowing in your own community. If you want a novel information or new information about a job, it needs to come from somewhere outside. So let's say this friend of yours with whom you were in second standard is now working in Google. So he is a better opportunity for you to tell you about a new job which you may find at Google. So that is the importance of weak ties. It helps in the flow of novel information or new information in a network. Let us look at the importance of weak ties in our case. So consider this example. Let us say the initial adopters of the technology are W and X, and the threshold for adopting A is 1 by 2. Initially whole of the network as before has adopted B. So can you apply your diffusion model here and tell me where, after what process will this cascade stop? So if you have done it correctly, you will realize that this community to which W and X belongs, this whole cluster adopts A, but W is not able to pass on the technology A to either U or V. So these two communities, they remain untouched by this new technology A. So here you can see the dangerousness of weak ties or bridges. They do not transmit the infection easily. But if you somehow make this infection transmit across these bridges, infection will really spread fast in communities where otherwise it wouldn't have spread. So keeping all these points in mind, let us look at some of the extensions of basic cascade model. Why do we need an extension for the basic cascade model? Let us start it with a small story. So how many of you remember this story of a priest and 3 crooks? This we have studied in our books when we were a kid. So the story was, there was a priest who was carrying a goat on his shoulders, and there were a set of 3 crooks who somehow wanted to get hold of this goat from the crook. So they made a nice plan. What 3 of these did, they stood at after some distances on this priest's path where the priest was going. First of all, first crook approached the priest and he asked the priest, "Why are you carrying a dog with you?" And the priest said, "It's not a dog, it's a goat. Don't you see?" The crook said, "Okay, it's fine if you feel it's a goat, but I think it's a dog," and he went away. As the priest moved further, after some time another crook came and asked the priest, "Why are you carrying a dead donkey on your shoulder?" Now the priest was a bit confused, but still he was quite sure that it's a goat. So he said, "Aren't you idiot? Don't you see it's a goat? Please get away from my path." Again priest started walking on his path. After some time, third crook came and again he asked priest, "Why are you carrying a lamb on your shoulder?" And this time the priest came into their trick. He felt that there is some problem with this goat. Maybe it is some magical animal or something weird is there. He left that goat and walked away, and the 3 crooks, they took the goat with them. So you see what is happening in this case. Here is a very interesting phenomena occurring which we call as social reinforcement. We have already seen previously that there is a threshold. You need some amount of people to tell you a particular thing before you can adopt it. So if your threshold was half and you are having 20 friends, so at least 10 of your friends should adopt this technology for you to adopt it. So if 2 of your friends say this, 3 say, 4 say, it doesn't matter. But if 10 of them say you this, you'll adopt that technology. The same thing is happening here. Now the question is, this threshold should not be equal for each and every person. Maybe if instead of that priest you were there at his place, even if 50 people would have come to you and told you it's a goat, you wouldn't have agreed. So all of us have a different threshold, and that is the motivation behind this extension of basic cascade model. So we changed the thresholds for different nodes and we convert it to heterogeneous thresholds instead of homogeneous thresholds. So here every node, consider a node V. So every node gets a different payoff for adopting A and for adopting B. So in this case, if you see, we have a node V. So if it adopts the technology A, it gets a payoff of A subscript V, and if it adopts the technology B, it gets a payoff of B underscore V. In this case, the value of threshold will be BV upon AV plus BV, and as you can see, the value of the threshold is node dependent. It is not equal for each and every node. Let us try to solve it using an example. So Again taking the same case, everyone in this network initially has adopted the technology B. 1 is the node which is the first one to adopt a new technology A, and this is the threshold for every single node which is written on their top. So can you carry out this simulation and then see what is happening in this case, how many of the nodes will shift to the new technology A. Moreover, when you are going to do this simulation, you are going to observe some very nice factors. So I am not going to tell you what are those factors. I need you to understand and observe and record all of those factors. Next, let us talk about knowledge, thresholds and collective action. Suppose you are deeply frustrated with some new rule of IIT Roper. Say a new rule comes up that 90% attendance is compulsory in all the lectures and you want to raise a protest against it. You also know that tomorrow there are some students who are going to do a hunger strike against it, say. So now what is your aim? Your aim is to collect a lot of people, collect a lot of students for this strike, because if you know if there are only 4 or 5 people in your strike, it's not going to work out. So in this case you need to do a collective action. We call such problems as collective action problems. Let us see how can we go about it. So you can convince a small number of your close friends to go to the strike, and these will be the friends whom you trust and the friends and your friends who trust you. But how are you going to convince the rest of the people to participate? It is going to be very difficult to you, and it happens because of the presence of communities in the network again. So you can convince your community or your friend circle to go to the strike and participate, but it is difficult for you to convince whole of the college. So if all of us are united, it becomes very easy for us to take an action. All of the problem occurs when we are divided into clusters and communities. And this is one of the biggest reason why high officials or companies, they use divide and conquer technique among its workers to suppress their unity. Let us see what do they do and what happens in that case. So suppose there is a company and all the employees, they want to stand against a rule made by their manager. Now we know that if all of the employees, they conduct a united meeting, they all together, then they can stand as a unit and they can oppose the manager. But now what this cruel manager does, he splits the people somehow in 10 groups. He makes 10 groups of people, let's say make them sit in different rooms, and these 10 groups of people, one group cannot talk to the other group, cannot understand what other group is doing. So what will happen in this case? Suppose none of the group likes the manager, even then they won't be able to stand against him. Why? Because one group do not know the opinion of the other group. So every single group will think that I am in the minority and none of the group will be able to take the action. So this particular thing is called pluralistic ignorance, where the people, they have wildly erroneous estimates about the prevalence of certain opinions in the population at large. So you know that I am thinking this or I want to do this, but you are not able to make a step because you do not know the opinions of other people and you have very, very different estimates about what they feel. Let's try making a model for this collective action also. So now every person in a social network knows about a potential upcoming protest against the government, say. We impart a personal threshold to every person. This personal threshold encodes the willingness of a person to participate. So if the threshold of a person is K, it means that if my threshold is K, it means that if K minus 1 other people, if K minus 1 people will participate in the protest, then I'll protest. Or if K people including me are in the protest, then I am ready to protest. But the process is not that easy. Let's make a bit complicated. So let's assume that the edges in the network are strong ties. So every person knows the threshold of his or her friends, right? But not their friends. So you know what is your threshold and you know the threshold of your friends. Based on that only you have to decide whether you are going to participate in a protest or not. So let's look at the first case here. There are 3 nodes. The threshold of W is 4. It means that W needs 3 other people except it to participate in the protest. So W is already out because it has only 2 friends. It cannot participate. Let's look at V. We need 2 other friends to participate in the campaign, but he knows that the threshold of W is 4, so he is not sure whether W will be able to participate or not, so V drops his plan. And similar is the process with U also does the same. So in this case your protest is not possible. In the second case, although every node has a threshold of 3, it means that every node only needs 2 other friends to participate in the protest. Even then they are not able to raise the protest. Can you see? So please take this up as a challenge and try to see why the protest is not able in the second case, while in the third case all of these people, they will be able to raise a protest. So this is much with the very basic material. In the next lecture we'll try to look at some of the advanced material.